In this video, I want to work on a program which computes true if the number n is prime and false otherwise. So I want to determine whether the number n is prime or not. In order to be able to do it, I need the modulo operator. So this is the operator, it's the percent sign, it's pronounced usually a mod b, and computes the remainder of a over b. So for example, 7 mod 3 is 1 because if you try to divide 7 by 3, you get 2 with 1 as a remainder. 8 mod 3 is going to be 2, 9 mod 3 is going to be 0 because 9 is divisible by 3. So in general, if you want to determine whether a is divisible by b, you would say if a mod b is equal to 0. And then if it is, then a is divisible by b, because a is divisible by b precisely when the remainder of the division a divided by b is equal to 0. So how would we go about this? Well, what we want to do is we want to try every possible divisor of n and say, okay, so if the remainder of the division of n by any number at all between 2 and n minus 1 is equal to 0, that means that n is not prime, but it's a composite number. If you can't find a divisor such that n mod a or n mod I is equal to 0, well, you're good, because if there is no such I, well, that means that n is prime. So, okay, how do we go about that? So we need to go through every possible divisor, but first let's take care of the special cases. So one special case is n smaller or equal than 1. In that case, there is no way that n would be prime, so we need to return false. Another special case, which we don't strictly speaking have to worry about, we can incorporate it later on, is that n is equal to 2. So we can say if n is equal to 2, then it's for sure prime because 2 is prime by definition. The next thing I want to do is go through every possible divisor of n and check whether n is divisible by that particular potential divisor. So how do we go through every possible number? Well, that's what for loops are for. So you would say for I in range, and we'll fix it up later, but in the meantime I'll say in range n. And here I'm going to ask, okay, so is n divisible by I? So I'll say if n mod I is equal to 0, so this would mean that n is divisible by I, so n is not prime, so that means we get to return false. And remember, once you say return false, that's it. The function finishes running. So it evaluates false and it returns. If n mod I is not equal to 0, the function is going to keep trying other i's, because it tries I equals 0, I equals 1, I equals 2, 3, 4, and so on. So it might return false eventually, potentially at the end. It might not. It might be that this is never true, in which case you'll never return false because you'll never reach this statement. So for that case, you need to return true. You need to return true, though, at the end, after you've tried all the i's. So this block is going to try all the i's, and then this statement is saying, okay, you haven't returned false yet. The way I know is because I've reached the statement. And now you need to return true because obviously you have not found the divisor for n, otherwise you would have returned false already. So you need to return true because n is indeed prime. Now let's fix this one up just a little bit. It almost works, but not quite. One problem is that if I is 0, this is just going to crash. There is no way to compute n mod 0 because division by 0 is not defined. Another problem is if I is 1, n mod 1 is going to be just 0. Always, because everything is divisible by 1. So what to do about that? Well, one possibility is to go n mod I plus 2. That creates another problem. What's the largest number that we try to divide n by? That number must be smaller than n, because n mod n is going to be 0. So let's do it systematically. What's I plus 2 right now? I plus 2 right now is going to go from 2 to 3 and so on up to n minus 1 plus 2. We want it to go up to n minus 1 without the plus 2. How to accomplish that? Well, subtract 2 from here, and then I plus 2 is going to go from 2 to 3 and so on up to n minus 1 without the plus